So yeah, good evening, guys. And today, so I love statistics, you know that. So today we'll be discussing about MLE, and I believe my responsibility is to share about, I mean, everything about MLE that I think you should know the story behind MLE and how the story evolves because everything has been done in the past and if I have time, I will show you the papers and all the works that has been done. So there's a story of how Emily developed over time, and I will be sharing that with you. But I need to start with uh, the revision and how MME started. That was done in the last class. If you remember, if you know remind yourself the fundamental problem of estimation. So you have a population, and you're assuming that samples are coming out of it, like x1 all are IID. So you assume that the population follows, every element of the population follows some law. This is a mathematical setup. Okay, this is a whole model setup. Some distribution f with certain parameters theta 1, theta 2, theta k. This is a law which where theta, like where you don't know theta 1, theta 2, and you're taking out samples. The samples are random variable because every time you're taking up a sample, it's different. So therefore it's considered random variable. And using the sample, so the goal is what? The goal is to estimate or get an idea about theta i's, oops, theta i's, which are unknown. So here theta i's are unknown. The f is also unknown, or f is known maybe. The theta i's are unknown. F is known. Sometimes f may be unknown too, but here we will assume in parametric statistics that f is known. So what we do, we try to form a function of this x1, x2, xn, which is nothing but a statistic. I think it's discussed before. Statistic or estimator, which is believed to give a close idea about the theta I. Each fi will give an idea about theta I. This is a fundamental goal. Close. This close thing is very subjective, and that's why different theories have come up. And we will see that how mathematically we'll deal this, because you know that there needs to be definitions about closeness idea. So this is very subjective, I should say. So we will learn that later also, but the first theory that you have learned is that um, the first method you have done is that MME, where if you want me to say it in one word, it's nothing but equate population moments to sample moments. Why sample moments? Because of WLLN fact. They're really, that is the goodness property. That's why they think they're close, since WLLN, it converges by WLLN to population moment. That's why they think they're close. So this WLLN fact is the closeness thing. Okay. In this case. And there are other cases also, but WLLN is the main thing. And then this gives how many k parameters? So k equations in k parameters. And then we solve for theta I, which we call as theta I hat. This is the estimators because the solutions involve xi, so fi, we get fi's out there. So this was the whole brief discussion about MME. Now, the question is that, So we always ask this fundamental questions, two fundamental questions. There are three fundamental questions. The third fundamental question, I will do it with the issue of when I go, like Fisher told us that. But the first two fundamental issue, and it also had the same issue is there with the MLE also, is that this you should know is that does always MME exist? Does always method moment exist? And the second question is that is method moment unique always? And these are two existential and uniqueness properties. This is something that we always we will keep on asking. Okay, so this one is existence, the other one is uniqueness, and we will show that it's not. ML is also not. We will give examples, and you need to know examples like this because these are fundamental properties, and of course this can come, as in exams. I mean that's not the fun, but I understanding is the fundamental idea. So all of you okay with this whole thing till now? Say yes or no. Good. So does always MME exist or not? So MME always does not exist, and it's very simple to understand. The simple to understand idea is that, see, we are equating population moment with sample moment. What if the population moment is not dependent on the parameter? So we will equate sample moment is equal to something which is not in the parameter. It does not contain the parameter, so it will not give anything useful, right? Can you give an example like that? So population moment does not depend on parameter. So we equate population moment to sample moment, expecting the population moment is a function of expecting of parameters theta is. But can you give an example of population moment where it does not depend on parameter? That is, x follows some distribution f of theta, yes, okay, but expectation of x, let's say, is independent of theta. Any example? Yes, okay.
T distribution with any degrees of freedom, mean is always 0.
T distribution will end me in. So that's a good. That's a good description. You're right. So T distribution with n degrees of freedom. That's a good example. Nice. So yeah, that's a good example. T distribution with n degrees of freedom. Another example can be, it's a very good example. I like that. I appreciate that. Another example can be where xi iid follows uniform minus theta comma theta. So expectation of the xi's is 0, right? So what we are doing by method of moments, we are equating 0 to 1 by n summation xi. And it will never be true, always. So therefore, we are not getting anything out of this theta, out of this method, right? Maybe we can get if we equate theta square, like the variance with respect to, if we explain variance with respect to the summation xi square, but the first moment method fails. Okay, so maybe we can extend this. The idea of extended method moment square. So we can extend this as, if something does not give, then we extend it to the next moment. If nth moment method fails, then move to n+1 moment method. That can give an idea, but the basic core idea of MME, the definition of core definition of MME, if you remember, is that we equate the first k moments. Okay, we equate the first k moments. So that this was introduced by 1984, 1894, sorry, 1894 by Carl Pearson, who also discovered the Pearson chi-square. So, so therefore, these are the two examples where the first k moments to equate the MME, but this can be extended. This can be the generalized version. If it does not happen, go to the next one. That's it. I mean, if one does not give the information, go to the next one. So in generalized moment method, one can show that it actually exists because it will naturally exist. If none of the moments exist, then that can be hard. Can you give an example where none of the moments of the distribution exist for a given theta? Any example? Do you know about that? So this is a third question. On none of the moments exist for Cauchy, but that's for Cauchy 0, 1. Is it okay? Like none of the moments exist for Cauchy for any theta? Yeah, fractional moments too. So what to do in that case? So what do we do in that case? So we cannot say that Cauchy distribution has a method of moments, because for the method of moments, we need to assume that the population moments exist. Otherwise, there is no sense in doing method of moments, right? So I can show you one example. If you remember in calculus, we did an example where e to the power minus 1 by x squared. This has, all derivatives 0. So maybe you can extend this to a, if you remember, if you can extend this to a distribution where all the moments can come out to be 0. But I don't think so that will happen, because, yeah, maybe you can think about it. But I don't think this will happen because it's all positive. For the second moment, always it will be positive. So, yeah. So it was a thought. I'm not sure about this, but it was just a thought that can you build a distribution? This was a, it can take the research question that just, or you can research on internet that can you think of a distribution with parameters theta 1, theta 2, whatever, theta k, whose moments are independent of theta I, but exist. If you can find a distribution like this, then the method of moment estimation will never, always fail in this case. Okay. Yeah, SK.
Degenerate distribution at 0, all the moments will be 0.
No, but you should consider theta, not 0. That is the only parameter.
Mm.
0 is not a parameter.
Right.
Yeah. Degenerate distribution theta, expectation is theta, and all these things are theta. Okay. So you cannot think like that. But yeah, I mean, you should try out this method. So think of a distribution where all the moments, population moments, are independent of the theta I, but they do exist. Cauchy does not exist, because if it does not exist, then we cannot say that I mean, if it does not exist, then we cannot say that the method of moments exist. So this will give an example that where method of moments always fails. Okay. So think about this question. Okay, and let me know if you find any answer. This is a good exercise. So, okay, all of you understood this, guys? This why MME may not exist always. Not the generalized MME, but the normal MME. Yeah. Super. So the next thing that is a problematic about MME is the uniqueness of MME. So if you ask about the uniqueness of MME, I will show you an example. So let's think in this format that if x1, x2, or y1, y2, yn follows exponential theta square, so exponential theta square means you know what is theta square. I mean, you know what is theta square, right? So theta square is a positive quantity. Now the question is that what does method of moments estimator say? You know that the first moment is theta square. You know that, right? Exponential lambda expectation is lambda. Expectation of yi. So you estimate what? Y bar as theta square hat. So you get, therefore theta must either be minus root over y hat or plus root over y. Do you understand the idea? Yeah. So therefore theta must be then minus root over y hat or root over y hat. Oh, sorry, y bar. Right. So since y are all positive, y bar will be always positive because y are coming from the positive distribution. Y is greater than 0. I mean, exponentially defined for, the support is always greater than 0. So therefore there is no unique solution. But if you know that theta is negative or positive, then it's a unique solution. And that's where Bayesian statistics comes up, that you can assume a prior knowledge about theta. Then maybe you can get a better estimator. So this also gives us an idea of Bayesian where maybe prior knowledge about theta can be helpful. Yeah, SK?
So I have a doubt. So
Yeah.
rewriting theta can be equal to minus of root y bar and plus root y bar. So is it like estimate of theta square is same as square of the estimate of theta? Like how can we see?
No, theta square is in a general lambda, right? I mean, there is no, understand, method of moments is not related to parameters in any way. Method of moments is equate the moments and this population moment sample moments. This population moments may be functions of the parameters. Okay. For example, in gamma, alpha, comma, beta, the expectation is alpha by beta, right? So so essentially we get k equations which can involve different forms of the parameters, k parameters. So k equations and k parameters, which involve functions of the parameters, not always all the, essentially just one parameter or just linear of the parameter. You understand, linear functions of
Yes.
parameters. Okay, so
Yes.
it can involve any function of parameters. So We equate first moment to the expectation as to the sample moment, and then we mu1 is equal to y bar. That's it.
So it is not like estimate of the function. It is just
Yeah,
like
yeah. Estimate of the it's another estimation of the functions. You're right.
okay.
All of you understood this, guys? Yes or no? Our group is understanding. Okay, great. So this is the whole idea about this. These are the issues of MLE. Same issues exist with MLE too. It's okay. So here, SK pointed out a method that. So SK pointed out this method, this issue that is. So we have got a theta square ka estimate. Does it imply same as theta hat ka square? Is this the same? So the question is that if theta f of theta has an estimate, is it same or how is it related to f of theta hat? Is it the same? Rather, does MME produces that or not? So this was the question what Fisher was concerned about. So in the paper in 1920, 1912, 1921 and 1922 paper, Fisher tried to, so before that, the estimate was all method moments. And method moments estimator is closely related to the, the least square method. And at that time, ordinary least square was used to estimate the parameters of the regression, because linear regression was the problem. Regression was the problem statistics started with. Okay, Gauss did with that, and then came Pearson, and all these people started to understand regression because they were trying to understand the orbits of planets, trying to estimate the orbits of planets. Okay, so what is the best estimate of the orbits of planets? Unless the orbits of planets are elliptical in 3D, so the projection can be something different. So that was a problem. They started with regression. So, and then I will show you the papers papers one by one. So this was a 12th paper that I'm writing an article on it, so I will be sharing the papers link soon. So this was the first paper article where R.A. Fisher, introduced methamom, maximum likely estimator. And in the 1922 paper, he first used the word maximum likelihood. Okay, so you can see, you can see some ideas. We will do that today. So this is the first paper he did, and he'd also try to do it for more, parameters. But you can see this line that you can see the relative values of p will be unchanged by a certain transformation. The probability, the issue is that the uh, Fisher was already trying to focus on the fact that if you change the the values of parameters, the estimate should remain same. I mean, the change of the values, like f of theta ka hat is same as f of theta hat. So this was the thing he was trying to implement, and that was the problem in his mind, and that was the core problem in his mind. And um, in this paper, you can see I mean, in 1977, John Aldrich, he was doing a survey of whatever um, Fisher has done, and you can see that the problem was this. So I'm reading it out from here. So Pearson thought that the method of moments was easily applied than least squares. Fisher concurred. So, and if you come down this line, he made a virtue out of this, agreement with least square and method moments where he did to a different standard. So what the idea was that he tried to make understand the problem is to choose a function. So understand there is a function, density function or distribution function, which is indexed by theta, parameterized by theta, and there is a curve already. Okay, so the idea is to form a function that minimize that the theta that minimizes this. Now the question is that the x can be rescaled. Then Fisher observed that the value of theta that minimizes this y of xz, it was a regression problem still, okay? Not in this case, like not still probabilistic stuff. It's not same as that which minimizes the actual or original objective. So his reasoning was in rescaling, account needs to be needs to be taken of the change of the variable. So non-invariance is important in this paper and Fisher, but generally it was not important statistical literature he knew. So the goal was he was trying to address or make a method where the invariance, we will see the invariance property of the maximum likelihood estimator, that the invariance was a very important idea. And you can see that from this corresponding theta ka example, that theta ka estimate and theta square ka estimate. So theta ka estimate can be different and theta square ka estimate can be fixed in this corresponding example. So this is not a fully grown example, okay? But the core idea is that in this, by this one second, let me start the broadcast of the screen. So the core idea that I want to share here is that method of moments may not be invariant. That means if you obtain an estimate theta MME and put an f on this, it's not same as always f of theta hat. And the best example can be normal. Let's say x1, x2, xn. Follows normal mu comma sigma square. So, or let's say normal 0 comma sigma square. The expectation part will always give 0, that let's go to the theta sigma square part. So 1 by n summation xi square is sigma hat square, right? And if I replace this sigma hat by sigma dash, sigma dash is nothing but the same. So the thing is that is the estimate of sigma hat root over this. I mean, what is the estimate of sigma hat? Can we write like this or plus minus? Is it true? So the method of moments does not give a way to deal with it because it has, it has no information about that. I mean, we cannot say anything about theta. So we will hopefully I will share articles on how to, more articles on this to make, make use of more examples. But the goal is to understand that it may not be invariant, and MLE holds a very important property in there. We will see a property of MLE, that invariance of MLE. So that was the goal behind all this, the development of MLE and how Fisher thought about that. Okay, did you understand the whole idea? This is the idea of MLE, the invariance. Is f of theta hat is same as f of theta hat? Can we write like this? We can prove it that for MLE it holds, but MME does not give any way to do that. No other way to do that. Did you understand, all of you guys, what was the whole idea? Any questions? Yes or no? Good. So the lack of invariance property, was the main idea behind the introduction. It was from the aspect of regression. The lack of invariance property is the main difference. I will give more examples of that. Maybe I couldn't give proper examples to show you, but yeah, but the lack of invariance is the basic idea. Yeah. Okay. So what was MLE? So before starting the MLE, I should write something about, tell something about the law. Like MLE may seem very, a theoretical way, and I can give you some justification, but in mathematics, things develop in an inductive way, in a way of, I mean, there's some principles, some axioms, where like geometry was developed on Euclidean axioms, Euclidean geometry. Okay. And then there was the issue of the triangle inequality, and on the surface of the earth, the sum of the angles of a triangle may be more than 180 degrees. And therefore some axioms were changed. Similarly, in statistics, so these are the things we were taught in our master's second year. There was a special paper called Statistical Inference, Theoretical Development of Statistical Inference, or Philosophy of Statistical Inference. But I think this should be taught to you guys so that you understand where it's jumping from. Actually, there are assumptions and there are axioms to understand how probability works. Okay. And one such axiom is nothing but the law of likelihood. And that's where the whole thing stems from. And this was introduced by Fisher. And you will see this law of likelihood always everywhere. Everywhere you will see this. You will see this in testing a hypothesis. You will also see this in NP lemma, insufficiency, and all these things will come up. Animally, all these places. So, what is the law of likelihood? What is the law of likelihood? law of likelihood says that if you have a sample like this, x1, x2, xn, following some distribution f theta, let's say. So I'm writing this because there can be many theta. So it says that the evidence that means the data where so A and B are two hypotheses, let's say, or in this case, parameter values. Theta 1 versus theta 2. Let's say curl. A and B are two hypotheses, or hypothesis that theta 1 equal to theta 2. Theta 1 curl and theta 2 is equal to theta 2. Theta is equal to theta 2 curl. So I will write it down properly. So A is a hypothesis, B is a hypothesis. Let's say here theta curl is equal to theta 1 curl is a hypothesis. And here it's theta curl is equal to theta 2 curl is a hypothesis. Theta and theta 1 curl are known. It's saying that the likelihood, okay? So we define something called likelihood. The likelihood that is the data. So, okay, I will write this format, okay? So x is equal to x curl is nothing but the data. This means x1, x2, xn, x is equal to small x1 is equal to, this is the data, okay? This is the realization of the data. So likelihood of this hypothesis A by data, by likelihood of this hypothesis B given data, that you know the data, is equal to understand probability of the data that x follows equal to given the hypothesis. Now, where is it coming from? This is a Bayesian connotation to it, that probability of data given A is equal to probability of A given data into probability of data by probability of A. So this gives an idea of, but there is an idea of, theta is constant here. So it says that, so this is one such way to understand that, but in a logical framework, it says that the evidence is the evidence, the likelihood of this hypothesis given the data by the likelihood of this hypothesis given the data is proportional, or is the degree to which the observation suppose the parameter value. Observation suppose the hypothesis. Understand that the observation is data suppose the hypothesis. So what it says is that likelihood is proportional of A of hypothesis is proportional to the degree to which or probability to which data supports A. This is the basic assumption. Just give me a minute. So likelihood of a certain hypothesis is proportional to the probability degree to which data supports it. This is the basic idea. The likelihood of a hypothesis, let's say, the likelihood of a hypothesis, let's say, yeah, I'm coming to the fact, I'm coming to the doubts. So a likelihood of this hypothesis that this student is good than that student is proportional to the, or likelihood of this hypothesis this student has IQ around this is proportional to the fact that the data supports the hypothesis, right? He's passed for in exams, and how this data of exams and all these things supports the hypothesis. This is the law of likelihood, and this is the whole theory is based upon this idea, the likelihood principle. So this is something that is an assumption. This is a principle, okay? And we don't take it like we think it's like in the past classes, all the Cheenta courses, like I didn't teach this thing because I thought it was too, too maybe difficult for the students. But I think I should teach this to the students because it's something they should understand. There's a principle on which the whole likelihood thing is based. The likelihood of a hypothesis is proportional to the probability or degree to which the data supports the hypothesis. This is a principle. Remember that. And it seems very obvious, or you can think as an axiom. Does it make sense, guys? If yes, write yes. If no, please ask me questions. Yes or no. What is your question? Please, unmute yourself and you can talk. Okay. Great. Any questions, guys? Did you understand, all of you? Does it make sense, guys? So likelihood of a hypothesis is proportional to the probability or degree to which the data supports the hypothesis. This is the whole idea, Yusuf. So this is how likelihood is defined. Yeah, this is how you can say this is how likelihood is defined. I mean, like there is no definition of likelihood in the in literature, but likelihood is defined in this way. Yeah. Now therefore, since it's proportionality, so therefore, yeah, this is the basic idea. So therefore, we say that likelihood of hypothesis A is nothing but probability x curl is equal to x given A. The probability to which the data suppose a hypothesis. That means suppose hypothesis means what? Given A, what is the probability x is equal to the what you have observed? Given A happens, what is the probability x gives output? It can be less if it's too unlikely. Let's say if theta is equal to 2 and you got that the value of x, what you have realized to be 1 lakh. The mean is 2, but you have observed the value to be 1 lakh. The probability will be less than. Did the screen get closed? I'm sorry. This is the basic idea. That likelihood is nothing defined but probability is our proportional to, so we can show it equal because we're only interested in the ratio. That what is the probability that we observe something, the random will observe the realizes that certain given value, given the parameter or given the parameter value or given the hypothesis. That shows that how much data is actually close. That shows that how much data is supporting the hypothesis. Is it clear with all everybody, guys? Yes or no? So you can switch over definition, but yeah, this is the basic idea. This was a likelihood principle. And since we're interested in the um, ratio, so we define like this because it can be any constant actually. Okay. Yeah, Niket.
So if we just summarize in one thing, one line like that, like if the probability x curl equal to x curl given the hypothesis is higher, that
So
means
yeah, that's the
the
next
data
part. That's the next
supports.
part. That's the next part.
Okay.
So this is called the principle of likelihood now. What comes up? That's a law. Sorry, this is a law because this is something. Now, the principle of likelihood is what Aniket is saying. That is what is coming up. That if likelihood of A given data by likelihood of B given data is greater than 1, is equal to 1 and less than 1, what happens? If likelihood of A is given data is greater than 1, that means that data supports A more than B, right? So A is supported by data more than B. So you can say A is greater than B. You can say A is equal to B and A is and B is greater than equal to. So it's like A supported more than B, both are equal, and here B is supported more than A. This is a likelihood principle, right? Did you understand, guys? All of you understood? Any questions? SK, are you understanding? Good. Abhirup, are you understanding? Kruti, Vaishnav, Anamitra, Ronak, Rahul, Shreya. Great. Sorry if I missed someone's name. So what is the process in MLE? Now it gives a very good intuitive idea, right? So now here, the basic idea is that, so MLE says therefore, the maximum likelihood. So we select, we have theta 2. Okay, I'm drawing this graphical way because it's related to Bayesian, this is related to graphical models in some way, but I'm not really telling you what it is. Okay. So we calculate the likelihood. So likelihood of theta is equal to theta 1 given data, and here also we'll do theta is equal to theta 2 given data. So essentially it's equal to, you know, the probability. So what we do is that instead of doing this, what if we write in one line? So therefore, there is a relationship with theta to probability, the likelihood of theta given data, which is nothing but probability of x is equal to x given data. Sorry, x is equal to x only data, but given theta. So observe, if you put in one value of theta is equal to a theta 1, okay, you get this is a, you know, certain value. Let's say you put theta is equal to 1, you get some output. Let's say, let's take an example. So we will take an example here. Let's say The first example is, let's say x1, x2, xn follows normal mu comma 1. So if you put values of theta equal to 1, you get what? The likelihood of theta is equal to 1 given data is nothing but probability x curl is equal to x given theta is equal to 1. So if you know given theta is equal to 1, you know the distribution. You're fixing the distribution of this. So therefore, this probability is nothing but the joint distribution. So it's probability x1 is equal to small x1 given theta is equal to 1 times dot xn is equal to small xn given theta is equal to 1. And you will find this probability because, so you don't find this probability, you find the joint density, okay? So here you find joint density or PMF, anything. Yeah, coming to your doubt, and you calculate this. So this will turn out to be a number, a single number. So if you vary this theta, theta is equal to 1, theta is equal to 2, the numbers will be changing. So therefore, this function likelihood is nothing but a function of some g of theta. So for different values of theta, we are getting different likelihoods. So we know that one likelihood is preferred than the other if it is greater than 1. One hypothesis is preferred than the other. One theta is preferred than the other theta if it's greater than 1. If this is greater than 1. So therefore, we will prefer that theta which is greater than all of the other thetas. We will prefer that hypothesis whose likelihood is greater than all the other hypothetical likelihood. So therefore, we maximize this. And we find for which theta curl T theta is maximized. And that's it. That's the whole idea. Did you understand? And you know how to maximize it by calculus or analysis. So this is the whole idea of likelihood principle, the principle of likelihood, the law of likelihood, and how MLE is found out. Yeah. Now coming to your question, what is your question? So I think I will first go to Shukrit, and then I will go to Yusuf, and then I will go to SK. Yeah. Please go ahead. Shukrit, please. Unmute yourself.
Hello.
Yeah, please go
Yeah.
ahead.
Yeah. So in that example, you are working with the n mu one, right?
Yeah,
So
M mu
for
1. Oh,
for
it will
that,
be mu is equal to 1. Yeah, please go ahead.
yeah. So here, f of x1 is capital X1 is equals to small x1, mu is equals to theta. It is the probability at the point x1, right?
No. I am talking about the density. So I told you I replaced f p by density. So in his paper he wrote f of x dx. So it's the probability that it's taking around that region. So I mean essentially f is calculating what? It's probability it's taking. It will take f times dx. We have done it in probability class. F times dx measures the probability that x will be around x. So this is what it's measuring.
Okay. Okay.
Yeah. So it's f not p. I mean essentially it's p, but it I mean the idea is x is around that small x. It's not x because that will be all 0. So it's density. Yeah.
Okay.
Yeah, you're right. Thanks for pointing this out. Yeah, Yusuf.
Can you please explain again from the joint distribution thing?
This example.
Yes, sir.
Yeah, I will explain that example more. Okay. The idea is that this joint distribution is calculated, right? I mean, this likely is nothing but a joint distribution now, right? This is the basic idea. F of x curl is equal to x given mu is equal to 1 is nothing but x1 is equal to x small x1, x2 is equal to small x2, or given mu is equal to 1. That is given the distribution, the xi follows normal 1, 1. So now we can find out the probability explicitly, and it will turn out to be a number, or the density. It will turn out to be a number. So for different thetas, we are getting different numbers. So for different hypotheses, we are getting different likelihood. Now we will select that theta for which the likelihood is maximum. That's a likelihood principle. This one. A is supported over B, data supports A more than B if likelihood is that greater than the other. Yeah, SK? What's your doubt?
Yeah. Can you explain once again why we are maximizing that? I didn't get?
Because likelihood of a hypothesis is more, like A is preferred more than B if likelihood of A is more than likelihood of B, right? Given data.
Right. Right.
So now what is G of theta? G of theta is nothing but the likelihood of theta, of the hypothesis theta. Theta is equal to 1 ke liye, it will give a different likelihood.
Oh, so we are considering different values of theta, and
So for different
like
values of
that.
theta, you will get different likelihood. Essentially, therefore, likelihood is a function from
Theta
thetas
getting
to
one.
real numbers, right?
Yes, yes, I got it.
So therefore, we are selecting that theta. So likelihood is nothing but a function from all
Yes.
the parameter space to real numbers, rather greater than equal to 0. It's a probability, it's rather 0, 1. All the parameter values, let's say this is a parameter space, all the parameter values you can take to 0, 1. So it's giving each parameter value one output. So therefore, we'll select that parameter value which maximizes the probability. That's it. Where data supports that value the most. Did you understand, guys? All of you? Yes or no? Right? Yes. Super. You guys are intelligent. Abhinav, did you understand? So therefore, let's see some examples of likelihood so that you understand it better. So x1, x2, xn follows normal mu, comma theta naught. Theta naught is known square. Theta naught is known, remember. So first step is writing the likelihood. L of mu given data is nothing but probability x curl is equal to x small x curl given mu is nothing but, or f is nothing but f of x1 is equal to x1 comma. I'm doing this for the last time because I'm writing the joint distribution because someone told that he didn't understand. I think Yusuf, because he joined late. So now this is nothing but this. The x curl is equal to small x curl. This is nothing but joint distribution given mu. Or so given mu, why we write given mu? Mu is not a random variable, but still we write mu because in Bayesian framework we assume it's random variable. So we just write mu, but essentially you can also write mu here because it depends on mu, but we write mu like that also. So it's nothing but since xi are all independents, IID, so we can write this thing. And so let's write this, let's compute this. So this is nothing but some constant sigma naught into exponential half x1 minus mu whole square by sigma naught square. Now this will continue till 1 by, yeah, the likelihood changes if you take the different sample. You're right. So that's why the theta hat will be dependent on the sample. That's the whole idea. See, understand that was the initial step. In method of moments of the estimation changes, right? So the estimator is actually a random variable again. What you get? Okay. So since xi sample changes, the sample is the probability distribution of the sample is nothing but joint distribution, right? So the joint distribution every time changes for different samples. So therefore, since the estimate is a function of the joint distribution, the estimation, like the whole thing changes. I mean, the distribution of the estimator changes. So that's where we come up to the next properties of when we say the estimator is good, because estimate is a random variable. So when we say it's, how do we know exactly that the estimator is actually represents lambda, theta well, the parameter as well? That's how the next weeks and the following weeks comes up, where we understand the good properties of the estimators. So anyways, this comes up. I hope it cleared your doubts, Shinjini. Oh, there's a minus half here. Xn minus mu whole square by sigma naught square. Great. So when you multiply it, you get, so when n equations are there, so when you multiply it, you get 1 by root 2 pi by sigma whole to the power n times exponential minus half summation of I from 1 to n. Exponential, summation a to the power x e to the power a into e to the power b is equal to a plus b. So xi minus mu whole square by sigma naught square. Now understand that sigma naught are known, so essentially it becomes a function of mu. And if you plot it, you get a distribution of mu. Let's say like this. So this is nothing but, you can see it's a summation of xi minus mu square, the summation of squares. So it will be like this. E to the power minus x is convex like this, and summation of squares are convex, like essentially, and it will not be a convex. It will be like this. So if you plot this up, it will be like this. Okay. As mu goes to minus infinity, this goes to infinity, this whole thing, and therefore this minus of infinity goes to 0, and as mu goes to infinity, this also goes to 0, and yeah, that's it. So find its a maximum. So this is g of mu, and this is mu. So you can see that for a particular value of mu, it maximizes. So what is that particular value for a given data? So you should write this mu, it's nothing but g of mu, so it's likelihood of mu given data. This given data is important. As data changes, the whole thing changes. So now we need to maximize mu, g of mu. So g of mu is, we got this, so let's differentiate g of mu. So this is a constant. So this does not apply to this is a positive constant. This doesn't apply to the whether it's like the maximality of this g. So we can replace, it's proportional to this constant, exponential minus half this. So what we do now is that, this is called likelihood given data. So you can see this, so you will do something called exponential family. So most of the distribution form are part of the exponential family. You will see that taking the exponent will really help. So they therefore define something called log likelihood. Because you will see that all these distributions, like they didn't know this, so they used log to reduce the computation. Because log is an increasing function, okay, for greater than 0, for domain greater than 0. So wherever this maximum helps, the log of the function maximum will be held at the same place, since it's a bijective function. Okay. So this is something you should be very comfortable with. Otherwise, this time. So wherever x ka maximum happens, the log of x ka maximum also happens at the same place. So therefore, if you take the log, it's called small l of mu given theta, log likelihood, is nothing but minus half, proportional to minus half, because it's given constant, summation of I xi minus mu whole square by sigma naught square. So therefore, we get the log likelihood, and if we take L of mu given data, is this. So we have to maximize. So we take the dash of it, and we take minus. So this 2 cancels. Summation of twice xi minus mu, and minus mu again differentiate. So we get this minus gets cancelled by sigma naught square. Now this log likelihood would be equal to 0 because we are maximizing it. And you can see if you differentiate it again, you will see that you will get negative stuff. So it's maximum. If you differentiate again, you will see negative. So L mu double dash will also be negative. So therefore, at this point, so it means that it's maximum. Anyways, for solving this, you will get, observe that mu, this multiply all sides by sigma naught square, so you will get, and 2 divide both sides by sigma naught square, so this gets cancelled. So again, it turns out that it's summation of xi minus mu. So if you divide it, it will be, if you take the mu outside the summation, it will be minus n mu is equal to 0, so equal to 0. So mu turns out to be 1 by n. So therefore, a good approximation of mu is nothing but 1 by n summation xi. So if you take xi the random variables, mu hat is function of the random variables is turning out to be 1 by n summation the random variables. So this is the mu hat, and essentially it's also same you got for method of moments. So we will see for a huge class of problems, method of moment estimator is almost similar to MLA, and I have made a video on that. I will share in the group, in our internal group. It's on the YouTube only. So all of you understood the example and the theory is clear of maximum likelihood estimator? Yes or no, guys? Any doubts? Please raise your hand. So if you revise, we have mu or parameters. We go and find the likelihood of parameters given data. In most of the cases, this is nothing but a joint distribution. Now then we find out the log likelihood, the L of theta given data. So rather I should write like this. So like that. And then we differentiate it. So we call it gradient, but with respect to theta of L, but we can differentiate it where you can say that equal to 0. And usually it's maximized. It will be local maximized Of course, it will be maximized. So here we put in all the, you know, del L del theta I, theta 1 is equal to 0 dot del L del theta k is equal to 0. All the individual ones. And then we don't compute the double derivative because it's usually give the double derivative is equal, it gives a maximum. And then we find theta 1 is equal to theta 1 hat is equal to something. Some f1 of the parameters x are the sample values. But usually in the derivative step, you must see that usually double derivative is greater than 0. Less than 0, sorry. You can compute it for your own stuff, but we also see the Hessian. In multivariate case, we see the Hessian. Hessian. Yes. Questions? So this is the whole method, and you should visualize this, and this is the whole chit sheet of likelihood with the examples. That's it. Oh, as I told, log was taken due to this reason that so all the distributions log note, all the we will do it in the next classes. All distributions, usual distributions, come from something called exponential family. In that exponential family, the density is defined as exponential. So all distributions comes from usual distributions. So naturally, in all of them, they saw that log transformation helps in easing the computation. Hence, they define something as log likelihood. Also, it has something related to other things like entropy and stuff like that, but that's something different. That is related to information theory. So I'm not telling about that, but usually they saw that this is the main thing. The log usually helps because it comes from the exponential family. That's it. Shukrit. Did you understand? Yeah. Ovido, what's your doubt?
Sir, sir, hello, sir.
Yeah, please go ahead.
Sir, you have given the sign of gradient theta log.
Yeah.
Sorry. Uh, yes, yes. Sir, why you have used this notation, this stuff, this
Oh,
kind of
because for
notation?
multivariate calculus.
Oh,
So
okay, okay, okay. Yes,
this is
yes,
same because
yes.
theta is a multivariate. It can be for normal
Hmm,
mu comma sigma square. Mu and sigma square are two variables parameters.
hmm, hmm,
And all this is same as nothing but this. All the partial derivatives are zero of the derivatives of the parameter. So you
yes,
can use this instead of this, but that's the mathematics. So essentially, you should
yes.
remember this graph to do this. But once you do this, it will be over in your veins, and in your whole procedure, it will be totally. But this is the whole idea. Yeah. Also, sometimes it is not differentiable, and we'll do that example. So we'll do that example now. But yeah, any other questions? All of you understood this? Yes or no? This whole thing, the process. Or if you have any other doubts, please raise your hand. Okay, great. Now let's do some more examples. I'll be usually doing the normal thing. You should do all the homeworks of the MLE part, and I have uploaded the homework in the Google Classroom and also shared in the group. So essentially, you will see that do the MME computations. So next day you will do all the MME computations of the all the distributions I have shown to you, and the corresponding MLE computations of the distribution. Okay, and you will see whether they matches or not, and they matches most of the time. So yeah, so I will do another two examples. So x1, x2, xn, we have seen for uniform minus theta comma theta, the MME estimate does not exist, right? The MME estimate does not exist because the x bar is comes out to be 0. So let's try to compute it by maximum estimator. This is the some important technique I'm going to tell you today. So remember that, and that's very important. So this technique is very, very important. So remember that, and you will need it a lot of time. So understand that. So let's say you are told that from minus something to plus something, a few data is taken uniformly, and you have got the estimator minus 5, minus 5.3, 4.1, minus 2.1, 3.7, and 6.3. So can you tell me what can be a good value of theta, an estimate of theta? Acha, can theta be, like, let's guess, can theta be 3? Can theta be 3? Yes or no? Let's try to understand, Shukrit. Can theta be 3? Why? Please unmute yourself. If it's possible, I don't know. Please unmute yourself. Anyone wants to answer, please answer quickly. Why? You can unmute yourself and answer. Yeah.
So because the range of uniform the x1 and xn, like x1 to xn, it lies between uniform minus 3 to 3, and the range, the values that you have written is not between minus 3 to 3.
Very good. Very good. So it's not possible, right? So what can be a good estimate? 6.3. Why not 5 or 5.3? Because negative it's minus 5.3. Yeah, please unmute yourself and say.
Yeah, so if in negative it is minus 5.3, that means the sample value shouldn't go beyond 5.3, like positive 5.3.
Okay, okay, makes
We
sense.
know
Yeah.
that the sample it is 6.3, so it can be anything between minus 6.3 to 6.3. So we should consider whatever the maximum in the positive and whatever is
Okay,
minimum.
why is not 7?
It can be it could be at least 6.3.
Okay, it could be at least 6.3. So we will see that the 6.3. So what we are doing, we are checking the minimum. In this case, we are checking the minimum, and we are checking the maximum, and taking all the positive stuff. Positive. Take the positive of that. So that is 5.3 and 6.3, and then take the maximum among that. Right? So you can say maximum of a mod of minimum and mod of maximum. This is going to be a good estimate, right? Did you understand? All of you? I'm just giving an idea. We have not seen that it's true or not. If you take x bar is not a good estimate, right? We have seen that because x bar is 0 and x bar is minus, like it will not give a good estimate, right? But this is a reasonable estimate. So we'll see that this is a very important, this does not give by method of moment. So this is something very important. We'll see this coming up in sufficiency and everything because, I mean, yeah. So let's try to mathematically prove this. So how do we mathematically prove? And this is where a bit of mathematics comes up. So be careful here. So we have observed, let's say x1, x2 from uniform theta 1. So we first compute the likelihood, that is the joint distribution. Be careful here, be focused here. It's a bit of math, so I'm just asking you to be careful. A bit of probably. So it's nothing but this. Given theta, all are given theta. Now understand that f of x is equal to x1 of theta is, understand this, is not 1, but it's 1 if x1 is less than theta and greater than equal to minus theta and 0 otherwise. So how do you write this in a compact form? You write this as 1 or indicator x less than equal to theta and greater than equal to minus theta. That means it's 1 if x is lying between this or 0 otherwise. This is the basic idea. This is how you write it when the domain is restricted. For exponential, you write is lambda e to the power minus lambda x. Indicator x is less than greater than 0. So you write indicator of the support. Right? X belongs to the support. That's how you write it. That's it. So you can write any f of x is equal to this, is equal to the corresponding, gx, the density, indicator x belongs to support. All of you got this, guys? Yes or no? Yeah. This is very important. Please answer.
So can you
So
explain the last?
So yeah, I mean, if you, let's say, you know the density of, a distribution. So the density of the distribution is 0 if x is outside the support and gx otherwise. So that's what I wrote. If x does not belong to the support, it's 0. If x belongs to support, it's 1. Just like this. It's equal to 0 if x is less than equal to 0, right? For exponential lambda. So you can combine this as the density value, and it's only valid when it's inside the support. Where support is where the density is greater than 0 or PMF is greater than 0. So therefore its indicator x belongs to the support, because when it's belong to the support it's 1 multiplied by 1. When it does not belong to support, it's multiplied by 0. So essentially it becomes 0 outside the support. Did you understand? No? Yes? Not at all? Fully? Okay. All of you understood this? Yeah, Yusuf?
So where you wrote f theta x equals to x1 equals to 1, that is for the indicator variable or for the uniform one which you have taken the
It's
example?
uniform because uniform ke liye the gx is 1 always, right? Between, oh, I'm so sorry. Yeah.
Okay,
1 by
yeah,
2 theta.
no, now got it.
I'm sorry, yeah. By 2 theta. Yeah. Thank you. So therefore, the likelihood of this case can be written as 1 by 2 theta. And we'll see that uniform distribution doesn't belong to log likelihood, so we'll treat it differently. We'll treat it differently everywhere. In exponential family, in Sear, Kramer or bound, all these things. Indicator, the first one. So these are multiplied, right? So it's indicator x1, first one के लिए less than equal to theta greater than equal to minus theta times indicator x2 less than equal to theta and greater than equal to minus theta dot 1 by 2 theta indicator xn less than equal to theta and greater than equal to minus theta, right? So how do you do this? So essentially indicator variable of two functions, if you remember, is nothing but indicator of a times b. So it's telling that there are two sets a and b. So indicator of a times indicator of b is nothing but, so here it's 1, outside it's 0, and here it's 1, outside it's 0. So in this case a is 1 in this part. In this part a is 1 indicator but b is 0. In this case b is 1 but a is 0. In this case both are 0. So therefore indicator of product of two indicator functions, these are a and b, is nothing but indicator of a intersection b, that x belongs to a intersection b. So therefore if you write like this, the likelihood will turn out to be 1 by 2 theta whole to the power n, because they're n data points indicator, they're multiplied. So all of them belongs to minus less than equal to minus theta and greater than equal to theta, right? Did you understand this? This was the main step. The rest are easy. All of you understood this? Yes, all of you understood this? Yes or no? This was the main step. This looks bad. If you have doubt, please ask me. Great. This is the main issue, main thing. So always write in terms of indicator. That's it, okay? So now, one by 2 theta whole to the power n. So indicator that, so how can you say that all the set is less than equal to something and greater than equal to something? So understand in terms of computer. Oh, yeah, okay. So if you have a stack like this, so you know that this highest, all the are less than equal to this value and greater than equal to this value. So if you just specify that the maximum is less than this and the minimum is greater than this, then it automatically implies the middle one are always frequent this. So if the maximum is less than this theta, all the x1, x2, xn is less than equal to theta, and you say the minimum of x1, x2, xn is greater than equal to minus theta, it automatically implies the underwala one will always be between these two, theta and minus theta, right? Did you understand this, guys? All of you? Yes or no? If no, please raise your hand. If yes, please say yes. It's very important. It's very important, guys. SK, you understood? Sure. So the fact that a set is between two values, all the elements of set between two values can be represented as the maximum is less than that corresponding value, and the minimum is greater than that corresponding minimum value. Since the minimum is greater than corresponding minimum value, that value automatically implies all the values are greater than or equal to this, because all the values are greater than or equal to the minimum. And since the maximum is less than or equal to theta, and all the values are less than or equal to the maximum, that means all the values are less than or equal to the theta. Did you understand, Abhirup and Yusuf? If you say x and y are less than or equal to and greater than or equal to, or xy z less than or equal to and greater than or equal to 1, so if you say that there are 5 children, and there are 20 students in a class, and the maximum score of the student is less than or equal to 90, and minimum score of the student is greater than or equal to 20. And then, so this statement is same as taking out the highest scoring student, making the highest scoring student stand and saying that his score is less than or equal to 90, and showing the minimum scoring student and saying that his score or her score, or corresponding to vice versa, the highest scoring student, his score or her score is less than or equal to 90, and minimum student his score or her score greater than or equal to 20, is same, right? Because you have seen the minimum. So all the things, all of the other scores are greater than or equal to that minimum, and hence greater than or equal to 20. And once you set the maximum, all the other scores are less than or equal to the maximum, less than or equal to 90. So therefore, this entire thing can be represented as maximum less than or equal to and the minimum greater than or equal to 1. This information can be represented in these two formats together, this and this. Did you understand, Yusuf and Abhirup? Okay, good. So therefore, this thing can be represented as now 1 by 3 2 to the whole to the power n indicator minus theta less than or equal to the minimum of all the xi's, which is nothing but the x1 order star is 1, and the maximum of the xi's is less than or equal to theta, right? Or you can also say that indicator minus x1 less than or equal to theta and xn less than or equal to theta, greater than, theta is greater than or equal to this. Also you can say 1 by 3 to the power n indicator minus x1 and xn both are less than or equal to theta, both. So therefore the whole PDF turned out to be this. Let's try to draw it now. Both are less, it came out, in this case it came out, it's minus x1 is coming out to be here minus 5.3, so it's 5.3, and xn is coming out to be 6.3. So theta is greater than or equal to both, and these are numbers. So therefore what? Therefore theta is greater than or equal to maximum of both of them. If I say theta is greater than 1, theta is greater than 2, both the information implies that theta is greater than the maximum of them. Theta is greater than or equal to 2. So therefore we can write this as again indicate 1 by 2 theta whole to the power n indicator theta is greater than or equal to maximum of minus x1 and xn. So now if you draw the graph now, you will see of theta and this g of theta or L of theta. So you see that it's only defined, so it's 0, so this is a number, let's say this is the corresponding number, let's say this is a number called some xi, it's based on the sample, so it's xi. So before if theta is greater than or equal to xi, then it's 1 into this. If theta is less than xi, it's 0. So before xi, it's 0, and greater than or equal to xi, it's 1 by theta to the power n. So 1 by 2 theta whole to the power n is nothing but some constant times 1 by theta to the power n. So 1 by theta to the power n, I say it's decreasing like this. But since it's before greater than or equal to xi, you have to draw it like this. So therefore, the likelihood turns out to be this, right? And now observe, right? Now this is not differentiable at this xi, right? Others are differentiable. So observe that that's why its maximum is happening. That's why there's that's at that xi the theta is going to be the maximum. Therefore, argmax theta, that is the theta where theta is maximized of likelihood, is nothing but this xi, is nothing but this maximum of minus x1 and xn. Did you understand, guys? So therefore, the theta hat MLE is nothing but the maximum of minus x1 comma xn. Now this happens for different samples, so we made it a random variable. All of you understood this, yes or no? So therefore, in this case, likelihood is not differentiable. Yeah, Virup. Now, this is some examples. The class will go a bit longer, I'm sorry, but yeah. So we'll do similar examples in the whole, in the next problem solving session. But let's do multi-parameter case. That example 3. That x1, x2, xn are is normal mu comma theta square. Mu and theta are known. Okay. One second. So the likelihood, I will be just writing the statements. You please verify it because it's already a lot of time. It's almost going to be 2 hours after 20 minutes. But yeah, this is turning out to be, understand here there are two things. In that case, we took it to be root pi whole to the power n. But in that case, the sigma was constant. But here it will be sigma whole to the power n times exponential minus half summation xi minus mu whole square by sigma square. So by multiplying, we get this. So I am just writing this down together so that you can verify this later on. This is the basic idea. So you multiply all of them, and here mu and sigma are known. So this will not be a constant now. This will be a variable. But again, we take the log. After taking the log, we get some constant. So you can just say this is proportional to. So instead of writing this, you can say it's proportional to this. So you can say log is proportional to, therefore, minus n ln theta ln sigma. Sigma is greater than 0, so it's defined. Minus half summation I xi minus mu whole square by sigma square. Right? Now it's easy. Now you do that del L del mu is equal to 0, considering theta is constant. If you consider del L del mu and considering, like if you do this, considering theta is sigma is constant, that's how you do the partial derivative. You will get the same result, right? Because there you also assume that theta was sigma was constant. So you got mu is equal to 1 by n summation I xi. Because in the previous example you saw that assuming that you got is constant. But let's do the sigma part. Now del L del sigma. Now we will do, let's say, sigma square, okay? because we are getting a estimate of sigma square, because sigma square is here together. So what I will do is I will write as sigma square whole to the power n by 2. Okay, so it is sigma square by n by 2. So it's function we are doing with respect to sigma square. So we get, because it will be helpful for us because sigma square is the variable we are taking and it's useful. And we will see we can get a sigma estimate by the invariance property of MLE. So you take mu as constant. So in this case, if you do derivative, it will turn out to be with respect to del sigma square, it's minus n by 2 sigma square, right? 1 by ln sigma square d ln sigma square d ln x. I mean derivative of log x is nothing but 1 by x. So it's, since you have to differentiate with respect to sigma square, it's 1 by sigma square minus half summation. Now with we are differentiating with sigma square, it's niche hai. So it's 1 by x ka derivative is 1 minus 1 by x square. So it's become plus, and this becomes x square is nothing, x is nothing but sigma square. So it's sigma to the power 4. If you find it fast, you're right, it fast, because I wanted to, verify it at home, since it's easy. So we get these two things equal to 0. Now we already know that what is the value of mu. So we can put it here. So we put this mu here value. So what we get? Also, yeah, it's correct. So if we just do it, we get that 1 by n summation xi minus x bar whole square by sigma to the power 4 is nothing but n by 2 sigma to the square. So it's 2 gets cancelled, and sigma square gets cancelled, it becomes this. So it turns out that sigma square is nothing but 1 by n summation over I xi minus x bar whole square, which is nothing but sample variance. It's beautiful. That's it. So we get that the MLE turns out to be, MLE of sigma square hat turns out to be the sample variance, and MLE of mu hat turns out to be the x bar that you observed. Sample mean. Right? Yeah, it matches with MME. Of course, it matches with MME. So you will see a wide range. That's why the whole purpose of the exercise I have given in the group last day, because the whole purpose is that to check the MA whether the estimates are same or not. So when you see the estimates are same, the natural question will come to you that why are all the estimates coming out to be same? Is there a theory? And in fact, there is a theory why they are to be same. There's underlying theory. Essentially, it's doing the same thing with a certain condition. Okay, it's doing the same thing. MME and MLE are doing the same thing with a different way. That's I made a video on that. I will share it in the group, but that's the whole purpose, the whole idea. Okay, so that's it. So that's where it gives. So it's how you do it with multiple parameters. Now you don't check, like you can do Hessian and check whether it's maximum or not. You see whether Hessian see that it's negative definite. Hessian is 0, it means negative definite. You prove that, but that's not required at all, because you can do that for your multivariate calculus. If you want to revise a multivariate calculus thing, you can do that, and it's suggested. It's very easy. If you want to do that, it will revise a multivariate calculus. If you have forgotten, that can be a good exercise to remember that, and that will essentially make you remember all the theory of multivariate calculus of how to find the maximum minima. So Hessian and the f of x, fxx fyy minus fxy whole square, that thing. If you find that, that will be revision for that. So it's double thing. So you can do this as homework if you think it's like useful. And that's it. That's how you deal with multiple parameters. For other parameters, so the idea is that I put in the mu value here. This is one important step. So remember this step. Okay, all of you understood this example. So I did one parameter example, I did two parameter example, I did an example where it's not differentiable. So MLE is clear, computation of MLE is clear to all of you guys, yes or no? So remember, these three cases can occur, and you have to be careful that which one is this. So one parameter, two parameter, or where it's not differentiable. These three are the only cases that can occur. Other two cases you're differentiable, so you can differentiate. Otherwise, all of you understood. All of you understood. So we let's say revision stuff. We started with the issue with the MME revision, and then what was the issue with MME exist or unique. Then we see that when MME fails, and what was the history of MLE and the invariance property. We'll come to the invariance property. Then we saw law of likelihood. Then we saw what is the MLE, how to compute the MLE, and saw examples of MLE, one parameter, non-differentiable, and two parameters. That's the whole thing we have done today. And then now we will do the example of uniqueness, non-uniqueness of MLE, and non-existence of MLE. It cannot also exist. And then we will do good properties of MLE, and then the class will end. But this gives an entire theory of MLE, and you need not know anything more than this, just practice problems. Okay, so coming back to where MLE does not exist, it's simple. Just give me a minute. So the existence of MLE has a very weird, has a very weird what should I say? Connection to the set of the parameters, where the parameters lies. One second. So so we will see in we will do a theorem where we will see that we'll take closed variable, and that's very important. And one sec, just give me a minute. I have an example. I'm just trying to find a basic. So there are various ways you can show that Emily does not exist. One way is when you see that there can be multiple mu's. Okay. Another way is showing that multiple parameters, mode parameters and equations. Okay. So I will show you this example in the same example. So where we assume that xn follows uniform 0, theta. So mostly it's a mathematical issue. So we assumed fx distribution to be this, right? 1 by theta. If x is less than equal to theta and greater than equal to theta, 0. But also you can make it on open interval. You can also write this as and 0 otherwise, right? You can also make this an open interval that fx given theta is equal to 1 by theta, 0 less than x. This is also a valid PDF, right? Both the PDF are valid for uniform 0, theta. So forget about uniform 0, theta. Both the PDF are valid, valid PDFs. But if you take this, if you compute this, you will see that if you just take minus theta to theta, if you take minus theta to theta, the same thing. So the thing is that x never achieves theta and minus theta. So you will get the function to be, whatever you have drawn, you will get the function to be like this, open interval. Since x is greater than theta, it never takes the value theta. You don't know, sorry, it never takes the value. So it turns out this is that maximum of minus minimum statistics, that xi, if you remember, the xi. So here x is greater than xi. Okay. That means till this point, it's 0. For greater than xi, it's like this. And it never approaches the point. But you know the limit is that point. You know the limit as x goes to theta, xi, theta goes to xi. The limit is turning out to be that xi. The maximum of that value. That is where the maximum happens. But the maximum does not exist. Because at that point, the maximum, at that point, it's not defined. The maximum does not exist. Supremum exists, maximum does not exist. So there is no unique point. There is no point. You cannot pinpoint somewhere where maximum exists, right? You can find theta where maximum exists. If you just change this equal to not equal to and keeping it valid CDF, because at the points the probability is 0, so therefore it does not matter. Did you understand the idea? So it's a non-existence. It's a non-existence here. Did you understand the idea, all of you? Yes or no? So if you remove the greater than equal to less than equal to just less than greater than, the maximum at this point does not exist. So if you remove this greater than equal to less than equal to this and draw this, it turns out to be that its indicator, everything is same, just greater than equal to change to be greater than. It cannot be understood with another example. It turns out to this, it will be harder. I have to do the entire thing once again. Mathematics. So it's in this case it will turn out to be greater than. So that means indicator this, so it's 1 by 2 to the power n when x is greater than that, and before that it's 0. So it turns out to be this here and this. So when you try to find the maximum does not exist, because it's like 1 by x. And at 0, this going to the infinity, not infinity, but to a certain value. So the maximum does not exist. So the theta where it attains there is no theta where it attains a maximum. You understand? Because it's open interval, it's not closed interval. If it was closed interval, it would have attained the maximum, but it's open interval, it does not attain the maximum. So there is no theta, pinpoint theta where it attains the maximum, the likelihood attains the maximum. So the mathematical problem is not solved. So the even it does not exist for this given PDF. So what to do in this case? In this case, you change it to the closed interval. Okay, you change open interval to closed interval, so that unique maxima is found. Because a continuous function on a continuous function on a certain space have a maximum, unique have a maximum and a minimum for maths theorem. So it depends upon the parameter space. The supremum is outside the region, but supremum is not. Supremum may not be attained. The idea is a maximum or supremum is not attained at a certain point. Okay. So it's like if you take this function, it's one value. So it's asymptotically one, but the maximum suprema is not attained. Supremum is one, but the maximum is not attained at a certain point. It's attained infinity. Here it does not attain. So theta for which it attains the maximum, it's not there. It's even increasing. There's a supremum value, but it is not attained anytime. Did you understand, all of you? So mathematically the problem is not solved. There's no theta because at xi it's 0. So and at this point it's this. So there's always a point which is above this. So where is the maximum attained? There's no place where it's maximum attained, right? So there's no maximum of this function. The theta where the maximum is attained. So therefore it's related to the parameter space. And that's where all these ideas, this mathematical stuff actually went into the Bayesian statistics, because there is no such problem there. And there were all counterexamples about this in Fisher. It's called Fisherian or statistics or frequentist statistics. So there are all mathematical problems out there. For good behaving functions and stuff, it's good. But to generalize to another aspect, it was difficult. It was mathematically certain difficulties that are there. And this is all discovered by someone called D. Vasu. So he did all these counterexamples and stuff. So that's important. That's important. And this was the idea where the frequency statistics was good for well-behaving stuff, but mathematically it was hard. I know it has a lot of counterexamples and loopholes. All of you understood the idea? Yes or no? Others? Yes, can you understand? Abiru? Okay. Great. Now what's non-uniqueness? There are other examples too. Another example is for I'm sharing it to you. Therefore, yeah. So one example we've done more in the problem solving session. It's essentially due to this greater than thing. If you just take a parameter space, a support, if the support is not closed, you will face the issue. Closed means not like a closed interval. So there's open stuff out there. If the support is not closed, you will face this issue. If the support is closed, you will not face this issue. For example, you take shifted exponential and x greater than theta. So that will cause an issue. So you will see, we will do this problem there in the corresponding problem solving session. Yeah. So maybe I will share the screen with you and show. So observe that the support, take the example, since x is greater than theta, so you will get that the same thing will happen. If x is greater than theta, it will turn out to be the maximum that thing. And you see, if determine another version of the the same distribution where it will exist. So you have to make greater than equal to theta and x less than theta 0. So that's what you have to make. Okay. So that's it. So because the support is open theta closed or open theta open infinity. So that's why it depends upon the parameter space ka geometry. Okay. Did you understand, all of you? All of you understood? Shiny, did you understand? Okay. Now, non-uniqueness of Emily. It's very simple. This is something very simple. So it's also like the same uniform distribution. See, x1, x2, xn follows uniform theta comma theta plus 1. So if you, I'm just writing down the steps. So if you do the same thing, the likelihood will turn out to be 1 indicator theta theta. So understand that it will turn out to be theta less than equal to all the values less than equal to theta plus 1, which can be written as indicator minimum of xi, that is x1, greater than equal to theta, and the maximum less than equal to theta plus 1. Right? So it's same as you got indicator theta is less than equal to x1, the maximum minimum, and greater than equal to xn minus 1. So therefore, you will see that it's indicator. So therefore, likelihood will look like between xn minus 1 to x1, it will look like a constant. So all this rests 0. So all these values inside, its maximum, it attains 1. So therefore, it's, therefore theta MLE belongs to this set. Open or closed interval depends upon the how it's defined. So it's not unique. Okay, guys, all of you understood this? So you can make notes of all these statements and the examples, and you know the methods how it's done. So that's it. Like that will be a good cheat sheet. All of you understood this, guys? Yes or no? This is easy stuff. So done one parameter, we have done non-uniqueness, we have done non-existence. Good properties. So we'll see by good properties, we will see that good properties will see that sufficiency, completeness, UMVV, all these are good. Consistency, large sample. These are called small sample properties. Small sample. It's called large sample properties. Asymptotic normal. This is the large sample theory. There are two different theory, like behaviors. Like we say n tends to infinity when the sample size tends to infinity. So under certain conditions, it's sufficient. Its completeness, its CMVV. I mean, if it's unbiased and it's consistent, it's asymptotic. Asymptotic normal. And these are certain properties you don't know the definition, so I'm not telling you. So the invariance property is this. Can you just give me a minute? So the invariance property is this. It's very interesting. Nothing that f theta hat MLE is nothing but f of theta hat MLE. Okay. So that is very useful. And yeah. For example, if you, let's say x1 x2 xn follows Bernoulli P. Let's say you want to understand whether probability xi greater than, let's say, certain value, or xi something, or xi follows exponential lambda. So let's say probability xi greater than or equal to 1, or let's say probability xi equal to 0. This is a parameter in itself, right? You know, estimate what is the probability that xi is equal to 0 or xi is equal to 1. That may be a good choice of yours. This is nothing but a function of the lambda, right? Because the probability contains lambda. And once, so you can find out the lambda hat MLE, and then you can find out the disca hat by doing disca hat, f of hat. So essentially the invariance property is very important and it helps us to find better estimates. So the good properties, but these are certain bad properties of MLE which can mathematically intractable, but it's useful on the whole. That's it. This is all about MLE. I will show you. Any doubts, guys? Yeah, Aniket?
Sir, xi follows exponential lambda. So probability xi equal to 1 must be 0, right?
Oh,
So continuous.
yeah, I'm so sorry. Let's say this.
Okay.
Yeah, thank you. Yeah, or maybe this. So essentially, it's trying to find out any probability, let's say it's a function of the lambdas. All of you understood this, guys? Yes or no? Yes. So you have discussed all about exponent, like we understood the reissues of MME and we revised MME. Then we've given our research problem to you. Then we discussed about the history of MLE and the invariance issue and the law of likelihood. And then we defined MLE. We did some one parameter example, two parameter example, non-differentiable example. We saw where it's where the non-uniqueness and non-existence of MLA, and then we saw some good properties and invariance, and we saw that how it's useful. Now we will finally show you. So thank you for staying till this point. So now I will finally show you the final thing, that when MME is equal to MLA. So we have made one video out here. If MME is equal to MME method of Cheenta, if you search it, you will see this 13 minutes video. So regarding, I will just tell a little bit about maximum likelihood M, and I will show you some things. So you will see that how the whole thing is, what is the MLE, okay? I have discussed it over here, log likelihood, and we will see that what we are minimizing. So essentially in MME, and so we have seen all these things are same in method of moments estimator. So essentially in MME, we are minimizing this, and MLE we're minimizing this, some summation of something, and in MME we are using this, and we get it to 0. Okay, that's what log likelihood is all about. And we're getting I equations. If you remember, for MME we will get I equations for k, like k equations for k parameters. In MLE, those k equations nothing but after differentiating the k equations, after with respect to k differentiations, the k equations are coming out equal to 0. So what is the similarity? The similarity is nothing but, if you see MME, which is for theta for all I, okay, k parameters ke liye we have k equations like this. For k parameters, you have k equations like this. So this is the basic thing about MME and MSE, the connection. You see the things are, the functions are different. So the connection is that it's 1 by n summation xi, and this is what we will learn about in while doing simple. This is called the score function, and the score function is nothing but saying that the expectation of certain things are 0. And this has a very big influence. You must watch this video to understand. And this h of x has been done a lot in Fisherian statistics, and you must see that how they are related to each other. You must watch this video, and we'll do more about this. And yeah, if you just take, so the idea is that for different h, for different things, h is different. So they are the same method actually. Okay, the underlying thing is same. We are taking different functions. Okay, and that's the best part. It's both are connected to each other, and that's why that's a beautiful aspect of it. The same thing under the same expression. So yeah, so that's it, and I hope you will enjoy it, and I hope you enjoyed this session of MLE, because I have to create a lot of things for this, and I think this is a very complete thing about MLE, and nothing more is required. And yeah, thank you guys, and if you have any questions, if you enjoyed the session, drop a boom. Yeah, thank you. So this was very good. I like this session. Oh, thank you guys. Thank you for staying till this point of time. Yeah. Thank you. Yep. So bye bye guys, and I will see you in the next session. Yep. See you sometime. So tomorrow it will be mostly problem solving of MLE and MME and understanding the connection. Do more problems and understand the methods. So the idea is that if you remember that graph I made, just remember the graph and make that as a note and cheat sheet, and everything will be falling into place. And for each of these examples, non-unit on this, all these things, let's write the example, and that's how you make your cheat sheet. So the method, the likelihood principle, the method, and all of these properties, make an example so that you remember that. Okay. So that's it. Yeah, what is recording? Yeah, I will see you in the next class, and yeah, thank you for staying till this point of time. Yeah, good night.